Well, now we're going to move into general plane motion. So let's just review just a bit. We started off with translation. And in translation only, it moves in either the x direction or the y direction, or a combination. In other words, could be both. We came up with mass times acceleration vectors. But we found that in translation only, it wasn't actually rotating at that instant. So the I alpha portion of the equation goes away, and we just had to deal with some of the forces in the x as mass times acceleration in x, some of the forces in the y as mass times acceleration in y, and then our moment equation was simplified because we didn't have the I alpha term. In rotation, we started with fixed axis rotation about the center of gravity, and in that case, we didn't really have any forces. We only had this moment equation about the center of gravity. Then when we moved into fixed axis rotation about something other than the center of gravity, we had a different form of forces. We did in the normal direction and in the tangential direction, but we still had to worry about some of the moments about P now, and use the parallel axis theorem. That worked out pretty well for us. In general plane motion, what we'll find is that we have to use the long form of the moment equation. We'll still do some of the forces in the x, some of the forces in the y. If some of the moments about g equals ig alpha works, then obviously we should use that. However, many times we'll be using some of the moments about p and using the long equation here. And sometimes we'll still have four unknowns, and we'll have to have an acceleration equation, and we'll recall the general acceleration equation from chapter 16. Acceleration of a is acceleration of g plus alpha cross r of a with respect to g minus omega squared r of a with respect to g. So we may use that equation in the cross product form, or we may use it in the scalar form of a of a with respect to g in the tangential direction, and a of a with respect to g in the normal direction. All right, so let's talk about a couple of examples here. Let me get my paper straight. Let me put these guys over here. All right, so here's a fairly easy problem from our textbook. But let's say these two guys are trying to lift this heavy ladder or this plank or whatever it is. He's going to lift it up with 40 pounds, and he's going to lift it up with 30 pounds. It only weighs 50 pounds, I believe. The plank weighs 50 pounds. So clearly, we've got 70 pounds lifting it up. It only weighs 50 pounds, so it's going to be accelerating in the y direction. But because he's got more force than he has, we can expect that it'll have some angular rotation, some angular alpha in that direction. So we're going to model this as a slender rod, and we know that the IG of a slender rod is 1/12 ml squared. So let's draw our free body diagram. We're going to say that we have 40 pounds going up, 30 pounds going up. We have an mg from the middle going down at 50 pounds. And if I sum the forces in the y direction, the only forces I have in the y direction are shown here on my picture. So I got 70 going up, 50 going down, 50 pounds is my mg, and that's going to be my mass, is 50 over 32.2. That should be times ay, not equals ay. Let me just erase that. 50 ay, and I get ay is equal to 12.88 feet per second squared. Okay, so that's obviously very easy. How about the rotation? Again, that's fairly easy in this scenario where, well, first of all, let's find out our x's. Some of the forces in the x direction is mass times acceleration in the x. Do we have any forces in the x? I don't see any written on in the picture here, so we can conclude that acceleration in the x is 0. And now the moment, try to find alpha. Again, I can sum the moments about any point, but I just have to be cautious. And I have got mistakes here. This is some of the moments equals I alpha. All right, so let's keep on going here. Some of the moments about g is equal to ig alpha. So in my picture, if I call this my positive direction, I can say 40 times that distance, which would be 7.5, is minus 30 times this distance of 7.5 equals my IG of 1/12 m, L squared is 15 feet long. Find alpha is 2.576. And I defined it in going in the clockwise direction as positive, so I'll put here again positive clockwise. All right, I summed moments about g in this problem, and it worked out really straightforward, but can we sum moments about another point? For example, point B. And the answer is yes, we can, but we have to be pretty cautious. The reason is because B is moving, and I cannot use the shortcut equation that we did previously of sum of the moments about B equals IB alpha, because this only works if B is stationary, meaning hinged, or an instantaneous center. In this case, it is neither. It is moving along with A, along with G, so therefore I cannot use this shortcut equation, and I'll have to use the long equation for moments. My sum of the forces in the X are still applicable. Some of the forces in the Y are still applicable. Some of the forces in the X are still applicable. The moment equation, in order to find alpha, I can sum this. I can do it about B using the long equation. So let's just look carefully at the picture. I'm going to go positive going in this direction, so I have a 40 going positive times this lever arm, a 50 going negative times this lever arm, and then on the right side of the equation I'll have my mass times acceleration vector times x bar, and then I'll have Ig alpha. Alright, so let's look at our equation. Some of the moments about B. 40 times 15, that's the lifting up force on the left side, minus 50, 7.5. That's going to be the mg times its distance. That's going to be equal to my mass, 50 pounds. The acceleration of g in the y direction I found from the previous work of 12.88, and the x bar is the distance from the center of gravity to there, that is 7.5. Now again, that is positive because I called it positive. I called this positive direction for this, and so that'll be a positive rotation for my mass times acceleration vector, so that's that. Plus Ig alpha is my second term, so Ig is 1/12 ml squared, and I can solve for alpha is equal to 2.576 radians per second squared. So I get the same answer, obviously. Put that up there. Alpha is equal to 2.576 radians per second squared. I get the same answer, which is what we want, a little different way. If I had done this way first, I would have had to probably, well, I guess it's about the same amount of work. I was going to say this may be a little bit longer. It has one more term in it, but whatever way that you want to do the problem, I'm sure would be is actually just fine because they all get the same answer. All right, this next problem is a little more complicated. This is a fundamental problem, 1718. And what we're going to have here is this bar is sitting horizontal in its original condition. The slot is frictionless, but we're going to release it from rest, and it's going to start rotating down and start moving a little bit to the right. What we need to find out, or what we're trying to find out, is that when theta is equal to 0, when it's like this, what's the acceleration of the center of gravity? What's the acceleration of point A? What's the angular acceleration? All right, let's draw a free body diagram of our bar in the horizontal position. So right here, we know that there's a reaction here, a force pushing up on point A from the slot. So I got an AY. I'll draw an AX in there. I've got my mg coming down. I'm going to stick with positive in the conventional sense here for all my accelerations and forces. So I'm going to say mass times acceleration of g in the x direction is that way, mass times acceleration of g in the y direction is that way, and positive alpha is going in the counterclockwise direction by convention. So let's sum the forces in the x and see what we get. Sum of the forces in the x is mass times acceleration in the x. Now if I look at the picture, there's only one force in the x direction, and because it's not being pushed by anything, and the slot is frictionless, I can say that AX is equal to 0. Therefore, my mass times acceleration is equal to 0, and my acceleration is equal to 0. So I know the acceleration of g at the point initially is going to be 0. How about in the y direction? Some of the forces in the y is mass times acceleration in the y. I got a positive AY, I got a negative mg, and that's going to be equal to mass times acceleration of g in the y direction. I've defined it as positive going up. I can solve this for AY. In my moment equation, I can sum the moments about any point, and let's try about g. Some of the moments about g is Ig alpha. So if I look at my picture again, I have a positive AY going this way, but it's going to cause a clockwise moment, and I define counterclockwise as positive, so that would be minus AY times the lever arm here of half of the distance was 0.3. Ig is 1/12 ml squared, and alpha. All right, so if I look at how many unknowns I got an AY, I've got an alpha and an AGY, and I need another equation. So I'm going to have to use an acceleration equation. So let's use our general form, but in the, our acceleration, our relative acceleration equation, but in the scalar form, which is handy for this. I'll just say acceleration of g is the acceleration of a plus the acceleration of g with respect to a tangential plus the acceleration of g with respect to a normal. All right, let's put all of our components here. Acceleration of g has an I component and a j component. Acceleration of a has only an I component, only going in the I because it can't be moving in the y direction. And then acceleration of g with respect to a in the, so this would be g with respect to a if it's going to be rotating in this direction, but I've defined alpha as going in this direction, so I'm going to say that r alpha is going to be that distance there, 0.3 alpha, and I'm going to say positive j, even though I expect alpha to be will become a negative number, but I'm going to draw it as positive because I've defined my positive directions that way. And then minus my normal acceleration would be 0.3 omega squared in the I direction. However, at the beginning here, and it would be going in this direction, but at the beginning, when I just dropped it, my omega is equal to 0. So this whole term goes away, and so this becomes my equation for acceleration. So I can combine my i's, and I got agi is equal to ai times I. I'd already solved for ag in the x, or ag in the I direction is equal to 0. So that says that aa in the I direction is also equal to 0. In the j direction, I can combine these, and I got ag in the j direction is equal to 0.3 alpha, and so I can get this relationship. All right, now I have three equations, three unknowns. I got those three equations that I can put together, and let's see, how did I do this? I set this equal to ay, I plug that into here, and I plug this alpha, I plug this alpha is equal to ag j over 0.3 into here, and I get a three equations, three unknowns situation here, and I solve for ag in the y direction. It turns out to be negative 0.75 g, which is negative 7.3575 meters per second. Plugging that back into this equation, and I get alpha is equal to negative 24.5. Okay, well, I hope that helps you set these things up. The most, well, it's several important steps, obviously, but the relative acceleration equation will turn out to be something you'll need to employ in several of the problems.